natural variability may be responsible for a small portion of climate change, such as orbital changes, volcanic eruptions or asteroids, sunspots, or rearranging of continents and oceans. In actuality, humans are to blame for majority of today's climate change issues, including activities of industrialization, modern agriculture, deforestation, and burning fossil fuels, coal, natural gas, and petroleum, increasing emissions of greenhouse gases. About 50% of emissions are from corporations such as power plants for oil and gas. As temperatures rise, glaciers shrink due to melting ice caps, with less precipitation equates to the inability to maintain glacial mass. Studying tree ring data, ice core data, glacial retreat, sea level rise, isotope dating, changes in the atmosphere, and weather phenomena allow scientists to measure and explain cause and effect. The changing climate is rapidly resulting in more and more extreme storms, heat waves, droughts, wildfires, temperature and precipitation patterns, shifting vegetation zones, melting glaciers, more sea level rise, and changing coastlines. When the Earth's orbit is closer to the Sun, the Earth is warmer, and when the Earth's orbit is farther from the Sun, the Earth is cooler. Simple, right? These variations also impact the swap of glacial and interglacial episodes within ice ages. More on that later. Without Earth's atmosphere, the average surface temperature would be below freezing. Greenhouse gases make up only 1% of air, though, keep the planet warm and make Earth livable. Earth's average surface temperature is 14 degrees Celsius or 57 degrees Fahrenheit. These greenhouse gases that trap heat include ozone, nitrous oxide, carbon dioxide, carbon monoxide, methane, and water vapor. The process in which the atmosphere heats the Earth's surface is called the greenhouse effect. Sun radiates waves into the Earth's atmosphere, and either get reflected back out into space or absorbed into the land, water, and air. Currently, there are more greenhouse gases than the Earth's land, water, and air can manage, increasing the heat energy in the atmosphere. Once in the atmosphere, it lingers as long as 300 to 1,000 years. Venus and Mars were both believed to be Earth-like billions of years ago. Venus' average surface temperature is 462 degrees Celsius or 863 degrees Fahrenheit. The clouds that cover Venus keep in all its greenhouse gases such as H2O, CO2, SO2, N2. Closer to the Sun than Earth, Venus felt the impact as the Sun brightened, oceans evaporated, CO2 was released, creating its runaway greenhouse effect. The sunlight warms Venus more because it is closer to the Sun and H2O doesn't fall as rain. Without oceans, CO2 stays in its atmosphere, all intensifying the greenhouse effect. The Sun's UV breaks apart some H2O, hydrogen escapes to space, oxygen molecules combine to make O3 in the ozone and continues to intensify the greenhouse effect. Finally, the remaining H2O combines with SO2 to make sulfuric acid, rain and clouds, intensifying the greenhouse effect and warming the surface more and more. Mars' average surface temperature is -47 degrees Celsius or -53 degrees Fahrenheit. Due to being such a small planet, Mars lost its internal heat. When its greenhouse gases did not replenish, water escaped and froze into permafrost and created a runaway cooling effect. H2O, CO2, SO2, and N2 from volcanoes stopped billions of years ago as Mars' interior cooled. Since Mars is farther from the Sun, it warms Mars less. H2O falls like rain and CO2 and SO2 dissolved into its oceans. UV breaks apart some H2O and N2, due to its weak gravity allowing low-mass hydrogen, nitrogen, and oxygen to escape to space, moving faster to achieve escape velocity. Removing H2O and CO2 reduced its greenhouse effect where oceans froze into permafrost and dissolved H2O and CO2. Records on climate only go back a few centuries, and the older the data is, the less reliable it is. Thankfully today, proxy data can be used from recorders found in nature, such as glacial ice, seafloor sediments, oxygen isotopes, corals, tree growth rings, and fossil pollen. The objective is to understand the climates of the past, in pursuance to compute its future climates and changes. The Keeling curve, derived from the results of Charles David Keeling's experiment that began in Mauna Loa, Hawaii in 1958, when the CO2 level was 315 parts per million. Keeling wanted to figure out where all the CO2 was ending up by measuring it in the air consistently over a long span of time. The Keeling curve provided the first significant evidence on the correlation of humans and their carbon dioxide footprint. Subsequently, the Keeling curve was a baseline for many studies on global warming. Later they found a direct correlation between CO2, temperature, and the rise in sea levels, whereas carbon dioxide acts like a thermostat and controls climate. And as time went on, a disturbing realization about where Earth's climate is headed began to surface. To date, the longest ice core ever extracted was 2 miles down from the ice sheet in Antarctica. After the analysis of many ice core samples, 8 ice age glacial/interglacial cycles were identified extending as far back as 800,000 years. From this data, scientists have established a climate graphic record and atmospheric data from that long ago. This information has been essential in assisting us when analyzing data from today, such as discovering that carbon dioxide from the past 800,000 years never passed 300 parts per million before the 19th century. Today, according to readings from Mauna Loa Observatory, the Keeling curve hits 420. As Earth is 72% ocean, an estimated 22 million tons of carbon dioxide mixes with ocean water daily, greatly impacting ocean acidification. Since the Industrial Revolution, the ocean's acidity has increased 30% and is on track to experience a pH decrease of at least 0.3 pH units by nearly 2100, a change not seen for millions of years. It has been discovered that seawater is acidic enough to dissolve some ocean animals' shells and coral skeletons. The ocean food web and ecosystems are directly impacted and struggling to survive. The CO2 levels are increasing too fast for the planet to handle. When it dissolves in seawater and forms carbonic acid, it lowers the ocean's pH. Currently, the amount of frozen carbon that would be released into the atmosphere is estimated to be 155 years' worth of current levels of fossil fuel combustion. Methane released from permafrost and the ocean floor is a great cause to be concerned. Derived from energy production, mining for coal and drilling for oil, waste, anaerobic bacteria in wet places, and agriculture, cattle farms and rice paddies, methane gas is 25 times stronger than carbon dioxide. It is about 20 times more effective at absorbing infrared radiation emitted by Earth. As permafrost thaws, the carbon-rich trees, plants, and animals that thaw along with it will rot and then create gases that will be released into the atmosphere, adding to greenhouse gases and climate change. In the ocean floor, when methane is released, small to large eruptions can occur. Recently, Arctic craters across Earth's surface have begun popping up, literally, due to methane bombs or explosions due to gases released. Glaciers are large masses of ice compressed from snow. They are identified as either a mountain glacier or alpine, found in mountain ranges, or a continental glacier or ice sheet, which is a mass larger than 50,000 square kilometers. Glaciers reflect solar radiation, keeping the Earth from overheating. An ice age alternates about every 100,000 years between warm and cold, or better explained, glaciations are periods when temperatures drop and ice sheets grow and spread out, and interglaciations are when climate is milder. Currently, although in an interglacial period, we are in an ice age called the Quaternary Ice Age or Pleistocene glaciation, which began about 3 million years ago. About 20,000 years ago was the last glacial maximum where most continents were covered in ice sheets and glaciers. Scientists recognize these 5 ice ages as monumental: the Huronian, 2.4 to 2.1 billion years ago; Cryogenian, 850 to 635 million years ago; Andean Saharan, 460 to 430 million years ago; Karoo, 360 to 260 million years ago; and Quaternary, 2.6 million years ago to now. Currently, the ocean sea level is about 8 to 9 inches higher now than it was a century ago because Earth has been warming. As our planet warms, glacier ice melts and makes its way into the ocean and raises the sea level. However, that is not the only way sea level rises. As Earth warms, the ocean is warming too, and water expands. Warm water takes up more space in the ocean and makes sea levels higher. Over 90% of sea level rise is due to the Greenland and Antarctic ice caps and sheets melting. Snow reflects back about 90% of sunlight back into the atmosphere, and the ocean absorbs 90% of the sun's rays. So with less ice, there is a double effect of less sunlight being reflected back and more being absorbed into the ocean, adding to thermal expansion in the air and waters. The glaciers are also melting from the bottom because the ocean is warmer. The pace accelerated from past decades to rising an average of 1.7 millimeters a year. However, since 1993, that rate doubled to 3.4 millimeters a year. High sea level rise will lead to permanent erosion and catastrophic flooding. Beaches, wetlands, and coastal areas will all be underwater. This sad reality is why humans need to act now to prevent any further catastrophic damage from our activities of industrialization, modern agriculture, deforestation, and burning of fossil fuels. What I found mind-blowing from our text is shown below in Figure 21.31. It lists IPCCs concerning effects and consequences of climate change, ranked in order of probability.